Hi everyone, welcome to the next video in the series. These next two videos are both going to be on the Fundamental Theorem of Calculus, which is one of the most, of course, fundamental theorems in all of mathematics. And really, when the connection was made to develop this theorem, it really revolutionized the way we think about mathematics and the way we think about calculus. Sir Isaac Newton, and Leibniz both independently made the connection between integration and differentiation. This discovery, this single discovery, this development fueled the scientific revolution for the next 200 years. And it is still regarded as one of the most important computational discoveries in the history of mathematics. So there are two parts to the fundamental theorem, and we've already been using the first part. It has to do with the definite integral. And then on the next video, we're going to talk more specifically about the other part of the fundamental theorem of calculus. So let's get going. So here it is. The fundamental theorem of calculus says if a function f is continuous on a closed interval ab, and capital F is the antiderivative of f on the interval from a to b, then the integral from a to b of little f of x dx is going to be the antiderivative at b minus the antiderivative at a. This is also called the integral evaluation theorem, the definite integral. It also, you see down here, the definite integral gives the total change or the net change of a quantity over that interval. This is the one we've been using before on the definite integral. So a quick review of this principle says set up a definite integral that yields the area of the region. And you can see the region is a parabola. And so the function, this is the function right here, and we want the area under that from this value to this value. So we would write the definite integral from -2, lower bound, to the upper bound of our function, and that sets up the definite integral. And then all you would do to evaluate it is you would integrate from -2 to 2. And remember that we put in the upper bound first, so we would say 8 minus 8/3 minus, and then we'd put a -2 in, -8 plus 8/3, and then find that out. Now, I put this screen on here because I wanted you to see that this is the fundamental theorem of calculus, of course, right here. The antiderivative, right? If you integrate the antiderivative, but I have small f's, these need to be capital F's, but I can't change it on here. But what I wanted you to see, this wasn't really important, is that this is just a math equation, that there's an equal sign between them. So that means we can move things around. So if we want to find f of b, right, we could just subtract, or add the f of a to the other side, and we would have this. If we're looking for f of a, we could find f of b minus this. So these are just math. These are just a math problem. So it has funky notation, but you could still rewrite them. So here's an example. Find the area of the region between the curve of y equals x to the third plus 1, between -1 and 3 and the x-axis. Sometimes instead of saying x-axis, they say y equals 0. So we would do an integral from -1 to 3 of x to the third plus 1 dx. Sometimes they say y equals 0. And then x to the fourth over 4 plus x from -1 to 3. So 3 to the fourth power is 81. And then I'm going to go ahead and change that, minus, and then this will be 1/4 minus 1. So this would be, let's do it on here, 69. That seems right. 69 fourths. And then this would be 1/4 minus 1, so -3/4 plus 3/4 would be 72 fourths, which probably reduces 36 halves, and that's 18. So we've done these before. These are pretty simple. Right. So here's a situation that we haven't really run across yet, but here's an example of a definite integral involving an absolute value. Now, absolute value, we don't have any formulas that allow us to easily integrate this. So, and you can see I've included a diagram of this function. So you could see the absolute value graph from 0 to 2, and it's just this area shaded underneath here is what we're trying to find. You can see that geometrically those are triangles, and we could probably figure out geometrically what the triangles are, but that's kind of, it's doable. But the analytical method to this is based on the definition of absolute value. So if f of x is equal to the absolute value of x, it's really a piecewise function. And it says that x is positive where x is greater than or equal to 0, and x is negative when x is less than 0. Okay, so that's the definition of absolute value. So this one up here, this 2x minus 1, is just a little bit different, but we can still find where this would be 0. We would just say 2x minus 1 is equal to 0, and so x would be equal to positive 1/2. Right? So that's going to be our dividing line. So if we define this as an absolute value, as a piecewise function, we would say that it was positive where x is greater than or equal to 1/2, and it is negative where x is less than 1/2, not equal to, right? It's not a function. So we're going to use that to integrate, and we're going to divide this up because we know it changes at 1/2. So we're going to divide this up 0 to 1/2. From 0 to 1/2, it is, here, it is negative. So we would say negative 2x minus 1 dx plus, and then we would say 1/2 to 2, it's positive 2x minus 1 dx. Okay, and so what you're seeing is the negative 2x is a negative slope, this has a positive slope, so we're writing it that way. And so then we would just say, I'm going to rewrite this one, 0 to 1/2 of negative 2x plus 1 dx plus, and I have not left myself enough room to work this problem, 1/2 to 2x minus 1 dx. Okay, and then integrate. So I have negative 2x to the second over 2, so negative x squared plus x from 0 to 1/2. And then I have plus, I would have 2x squared over, so this would be x squared minus x from 1/2 to 2. And then I want you in your notes, since I'm out of room but you're not, I want you to go ahead and finish the definite integral for both of these two so that you can see what they are. This is not overly difficult unless you just don't remember how you do absolute value. And so go ahead and finish this problem and we're going to move on. So let's move on. I want to cover a little bit more about particle motion. By the way, if you finished the problem, the last problem, which I'm certain that you did, you should have gotten 2.5 as your answer. So let's talk about this difference between the displacement of a particle and the total distance traveled over a particle. Okay, so the displacement of it has to do with its movement, and you can see down here by the picture, you know, the particle is moving along, it moves at one direction, it changes direction, and then it moves the direction again. This is the velocity, right? So the velocity, it's going to the right, then the left, then the right. Well, that's what it's talking about. It's saying, you know, we'll take the area of the first region minus the area of the second region, because it's going to the left, and then the area of the third region, and we would add those together and get a net. That's the displacement. But the total distance traveled by the particle doesn't matter. It doesn't matter whether it is going to the right or to the left. It's just a distance, right? Just a number. So in that case, you would take the absolute value of the velocity function. the absolute value of the velocity function, and you would, in essence, add the three areas together. So this is huge in calculus, that you realize which one you're talking about, displacement or total distance. So here's an example of particle motion where we've been given the velocity function in terms of time in seconds, and we want to know the displacement of the particle over the time interval from 1 to 5. So for A, what we want to do is we want to write the definite integral from 1 to 5 of t to the third minus 10t squared plus 29t minus 20 dt. Now, this is one of those lovely problems where I know you can do it by hand, but it will take quite a while to do that. So when you would integrate this in your calculator, you would go to Math. I'm having a hard time getting this to right. Go to Math, and then I think you pick like number 8. It looks like this, FNINT. And then when you get there, it puts all this, these are little blanks. It gives you spots where you can put in this information, type it in and get an answer. Okay, so putting it in like this, if you were doing a calculator problem, you would get 10.66666, right? And in calculus we round or truncate, so I probably would just do that. But then when you do B, B is the total distance traveled. So you would still set it up the same way. You would still have 10 to the third minus 10t squared plus 29t minus 20 dt. But because you wanted the total distance traveled, you would take the absolute value, right? And so you would type the same thing in. You would still do the function int, fill in the information. But when you got ready to do this part right here, so you have this, I'll use blanks this time. When you do this part, you want to go to Math and then arrow over to num, and you're looking for ABS. Now my calculator, even though when it puts it in there, it puts the absolute value bars in, but this is the function that it looks like. So when you do that, you get 11.8333, right? And if you're doing the calculus, 11.833. And so because those two numbers are different, what does that tell you? Well, it means that somewhere in there it's going to change directions. And so the displacement is going to be different from the area, because, or the total distance traveled, because it's going to have to change directions in there somewhere. So I use my calculator. Otherwise, it takes a really long time. I will have you do a few of them by hand just for practice because it's good with fractions, but really, otherwise it's extremely tedious, and it's really more important that you set it up properly. So there are many theorems that come out of the fundamental theorem of calculus, and one of them is this definition of the average value of a function on an interval. Fundamental theorem of calculus also came out of, since we're talking about definite integrals, came out of Riemann sums, because it's finding the area, estimating the area, finding the area under a curve, between the curve and the x-axis. So if f is integrable, I have a hard time with that word, integrable on the closed interval ab, then the average value of f on the interval is 1 over b minus a times the integral, the definite integral from a to b of f of x dx. And you can see a diagram down here where you have a function. Here's f of x. We're going from a to b, and here's the area under the curve. And so the average value basically is the height of this horizontal line. And this height of the horizontal line is this average value here. So this rectangle right here has the same area as the shaded region under the curve. And so for positive functions, like what we're saying here, we would say that the area divided by the width minus the height is minus the average height. So, that's finding the average value of a function on an interval. Okay, so find the average value of the function f on the given interval, right? So we have the function 1 over b minus a of the definite integral from a to b of f of x dx. Okay, so to find that, we're just basically, this is a, this is b, this is your function. And so we have 1 over 1 plus 2 times the integral from negative 2 to 1 of x to the third minus 3x squared dx. So this is just 1/3 times, and this is x to the fourth over 4 minus 3x to the third over 3 from negative 2 to 1. So this is going to be 1/3, and the first is 1/4 minus 1 minus, and then put a negative 2 in there, that'll be positive. So 2 times 2 is 4, 4 times 4 is 16, divided by 4 is 4, plus 8, right? And so this will be minus 12. This is negative 3/4. So our number is going to be negative. This is 48. So negative 51 fourths times a third. So negative 51 over 12. And if we reduce that, which we don't have to, it would be negative 17 fourths. Okay, pretty simple. So I hope you took good notes about the fundamental theorem. We're going to do some more definite integrals to practice when we get back to class. And then stay tuned. The next video will be on part 2.